Hello.
Hello.
The climate change and the river water management session will be started in 3 minutes. So before starting the sessions, I briefly explain the rule in these sessions. We have also 5 speakers, and each student can present in 12 minutes, and 3 minutes will be in the Q&A time. So we'll start the session 15:12, 20 to 20. So if you are ready, please turn on the video, please.
Hello, can you hear me?
지금 말하고 있는 건데 말을 안 한 이제 청중들이 말을 안 해서 그런 거 같아요.
I'll check this student. Green.
Hello.
Hello.
네.
I'm just checking my mic. Can you hear me?
Yes, sir. What is I will check the name. Lin Luan Bang. Please answer to me.
Yes, I'm here. Sure.
Okay, thank you. Sal Alisa.
Yes.
Okay, thank you. Luan Tai Dua. Luan Tai Dua, please answer to me. Okay, it's time. So it's the first topic is LSTM-based prediction of stream flow during peak rainfall event of Pioneer River watershed, presented by Kola Karin at Kyungbu National University. Please get started.
Good afternoon, everyone. I'm Karim Kola from Kyungbu National University. I'm currently being supervised by Professor Young John. I'd like to welcome everyone to the SWTIC presentation, and I'd like to present my research on LSTM-based prediction of stream flow during peak rainfall events of Pioneer River watershed. So the contents will go as introduction, aim and objectives, the literature review, a brief one, and the problem statement, the study area, the LSTM itself, the methodology, the results, future study, conclusion, and references. Well, application of data-driven machine learning models to hydrology is currently gaining momentum globally. We have had applications from text mining, neuroscience, telemedicine, and now if we want to apply these data-driven machine learning applications to the field of hydrology, we can consider stream flow prediction forecasting in order to simulate hydrodynamic behavior so that we can make informed policies for mitigating flood risk. Deep learning models offer accurate and simpler modeling solutions than normal traditional physics-based models. And then there is research concerning whether we should focus more on model accuracy or we should actually consider the knowledge-based hydrology, in the sense that do we need to have like a proper understanding of hydrology before we can introduce our deep learning algorithm. And then one of the foremost researchers in the person of Couch and Lane from the publication says in hydrology, however, hydrologists are not only interested in obtaining good predictions, but also in explaining the physical drivers of stream flow. These physical drivers could be digital elevation of the waterbed. We have to consider the level of transpiration of the river. We have to consider several other things as well. So the aim of the study is to predict daily stream flow of Pioneer River during the peak rainfall scenario. And we have several other objectives, one of which is to actually evaluate the model behavior. And then from the literature review, we specified about 90 keywords globally from the Web of Science and Scopus database, and we were able to generate this particular word cloud. Here, right here, we can see that each circle represents a certain keyword that we checked. And we discovered that the US and China actually claim the highest publications in the use of LSTM. That means when you search the internet, when you search Web of Science and Scopus, you discover that the US have more publications, most publications when using the keyword LSTM. South Korea and India have the highest number of publications when you use the keyword of AI and ANN. And then the problem, in August 21 this year, a certain resource center in Tennis, Venom precisely, actually experienced a peak rainfall in such a way that the Pioneer resort was heavily flooded after about 0.38 meters of water, which occurred within just 4 hours. And then so we took it upon ourselves to consider like how can we simulate this particular peak rainfall if we can obtain data and then probably adjust our model in such a way that it may make the true incident that happened that time. So here's the USGS data for that particular day, indicating that there was a very big rise in the stream flow, which also is reflected in the data as well. So we defined our program segment as given a historical window size of data of water level, rainfall, and stream flow. We want to predict stream flow fluctuations if this peak rainfall actually happens. So here is the study area. We have the study area was actually called out from the Dixon and Hickman counties in Tennessee. And here is the watershed of the Pioneer River, which is about 38.1 kilometers long, and it forms the tributary of the Duck River, and an elevation of 108 meters. So I do not want to bother you much about the LSTM. We all know it's just a type of recurrent neural network, which learns long-term dependencies using gates and cell states. That's the animation. And then for the methodology, we obtained data from the USGS website, and then we fill the missing data using climate data from NOAA. We observed 4 different stations from the NOAA, and we checked the correlation of the data. We were able to pick Centerfield station, which had about 0.8 correlation with the experimental data. We splitted it, then we researched it using Keras reversal on scikit-learn for hyperparameter tuning correlation analysis. We created the LSTM, and then we did the result analysis. Here is just like a yearly look at the data set. And then I explained this already. When you look at the autocorrelation, function here, we discovered that it shows that the stream flow observations actually correlated with the 50 lags of itself, and then at that point we did the confidence interval. We can extend it from 1 to like 25. Beyond this point, then there is no much correlation. So because of this, we decided to pick the sequence length. We want our model to go through the first 14 data points before we can make a prediction. And then we introduced the knowledge of hydrology, which is the main core part of the work, by considering precipitation and elasticity, which is a sensitivity analysis. We want to know how sensitive precipitation is to stream flow. And then we calculated this using the non-parametric precipitation equation from Romanian et al. 2001. We discovered that precipitation elasticity equals 2.3. This means that a 1% change in annual precipitation results gives about 2.3% change in mean stream flow. We will check this if our model can predict this. And then with the research we discovered that we varied the neurons, number of neurons from 5, 20, 32, 64, 128, and 512. We discovered that 64 neuron gave the lowest computational time of 3 hours 26, and then with actually the lowest mean square error. So we preferred this and we selected it as the optimal LSTM. So for this, we now change our treatment. We consider rainfall to predict stream flow to predict stream flow for 2 stations, upstream and downstream, then water level to predict stream flow, and then we consider all the full data to predict stream flow using the specifications of this workstation. And then here's we checked all the model losses and discovered that when we used all the full data, the model loss, the best epoch convergence happened at 50 for all the full data, beyond which actually there was no loss. The loss was constant. So we selected the full data treatment. And then if you have a look at the treatments, for the first LSTM model, when we used the input of precipitation only, we discovered that it gave a very terrible result based on the fact that it failed to capture the temporal dependencies of stream flow, which showed a negative NSC, indicating that the model is actually not predicting, it's only predicting, it's not predicting anything. And then the mean square error was actually too light. And then when we checked for the peak precipitation, we added 0.30 meters, which happened during the rainfall incident. When we added it to every single data point of the rainfall, we discovered that the result was still a very terrible one. Then we proceeded to the second treatment of stream flow only. We discovered that although the NST actually increased, but then it was still not capturing the temporal dependencies. We considered for the water level, which was actually better than the stream flow, but then it still did not capture the temporal distance. So you can see a lot of dispersions from the line of best fit. And then we consider the full data. If we combine water level, combine rainfall, combine stream flow from the 2 stations, upstream and downstream, we want to know how the LSTM will behave. The LSTM showed that it actually improved the NSC to about 0.55, and the RMSC reduced drastically, indicating that the model has started learning the temporal dependencies. Then we simulated the peak rainfall by adding 300 millimeters of water, which happened on that flood day, to every single data point, and then we checked if the LSTM could predict the peak flow. We discovered that the NSC actually added 0.6, improved from 0.55 to 0.68, which is still an averagely with a slightly better NSC than the previous NSCs from other treatments. So we wanted to check how the full data input LSTM predicted the stream flow. If you check the prediction error here, you can see that to a certain extent it's still slightly manageable. The prediction error is still not too significant compared to other models. But here there is an underestimation here. Maybe as a result of data leakage, we can still improve our model by inputting several other factors that drive stream flow. This could be elevation data, and this could be evapotranspiration data. This could be meteorological forces like temperature, like the wind speed, wind speed and all. And then if you check, then we compared to check the scale. We wanted to know if actually this model was actually better. Then we checked the scale of the LSTM, the optimal LSTM with the naive model. The naive model is the standard model where we can compare if your metrics of your model is actually greater than the naive model, then that means the model is actually predicting certain variable. So when we check, we have the final LSTM to give us a 0.68 NSC, and then the naive model was 0.55. The concept of the naive model is that it assumes that what happens yesterday, the stream flow of yesterday will actually happen tomorrow. This is just a basic comparison for performance, for model performance. So invariably, the LSTM actually perform better than its normal standard. So in conclusion, optimal LSTM model perform better than the naive model with about NSC of 0.68 to 0.55, I beg your pardon, 0.55. And then we observe that hydrologic knowledge can be infused into the model by introducing other static inputs like DEM, satellite observations and meteorological forcings as earlier stated. And then from our knowledge of hydrology, when we did, we completed the preservation elasticity to be 2.3%, it showed that actually the LSTM did not consider the preservation elasticity. Then after that, we can finalize that machine learning models may successfully estimate how to reach an computationally expensive hydrologic modeling applications without a physical model, or it will actually form an hybrid with the physical model. But this is only when it's being given hydrologic knowledge, like when given detailed information that governs hydrology. Currently, we are still considering a lot of future work because it's a work in progress. We're still looking at obtaining more data, and then we want to check the behavior of the input variable features using integrated gradients and Taylor's diagram, and then we'll validate our model using the SWOT simulated string flow. And then further research, we can also consider the length of training data, and then we can check how data on the deep learning models. References cited in the presentation and back here presented. Thank you so much for listening.
Okay, thank you. So if you have a question, please ask the question to speakers. No? Okay, so due to the limited time, I will invite this next speaker. Thank you, Kola Karin. Next speaker is Luan Sovan. So his topic is behavior of the sixth method for sediment transport capacities estimation of the spatial transport of solid erosions. Please get started.
Hello. So, good afternoon, Professor Chong and everybody. My name is Linh. I come from Vietnam. So today I present my topic is behavior of six methods for sediment transport capacity estimation of spatial temporal soil erosion. And my present has five parts. First is introduction. Second is study error and data availability. Third is methodology. Fourth is results and discussion. And finally, conclusion. So introduction. So soil is a key natural resource necessary for the sustainability of agriculture, industry, and hydrological biological system. Soil erosion is a major environment and economic concern affecting not only in Korea but all continents around the world. Soil loss due to heavy rainfall, wind, and human activities has been on the increase worldwide. So there are various problems related to soil erosion, such as ecosystem destruction, decrease agricultural productivity, increase riverbed deposition, and reduction of stream water quality. And soil erosion can be classified into three main types, like sheet, rill, and gully erosion. This natural process is caused by the dynamic activities of erosive agents such as water, ice, snow, air, plants, animals, and humans. Second is study error and data availability. Our study error is the change in Beijing, and the change in Beijing is located is upper part of the Zhangdang Beijing, and the area Beijing is 290 kilometers, with the mainstream is 28 kilometer long. The average slope is 0.246 and average elevation is 549 meters. This input data includes land use, soil type, and we can see there are 6 types of land use, and the mixed forest and mixed fields account the most areas. The soil types, there are more than 35 different types, and rainfall event we use 3 different storm events. They are historical events happened in South Korea in 2002, named Rusa. 2003 is Mami, and 2007 is Nari. Wisdom and the data meteorological data is we use hourly. And in our method includes 6 different sediment transport capacity. The first method is anglin-Hessian. The second method is killing reduction. And the fourth evident methods is slope and unit and discharge, effective stream power, unit stream power, and shear velocity. So this method is integrated in GSSA model. GSSA are graded surface, subsurface hydrologic analysis, is a physics-based distributed hydrologic and sediment transport model. So this is the structure of the model. So firstly, when rainfall happens, it has interception and evaporation, and when net rainfall attack soil surface condition, the infiltration start, and after a specific threshold, overland flow happen, and this will trigger the detachment by flow, and when net rainfall will trigger detachment by raindrop, and the total of detachment compare with flow transport capacity to decide which cell is erosion or deposition. So in our model, we use nine parameters. They are sensitive, and we use SCI method to auto calibration. So in order to evaluate model performance, we use 4 different statistical indicators: R-square, RMSE, PBS, and VCI. And this is the result. So as we can see in the calibration procedure, 4 values of the statistical indicator illustrate high agreement between the observed and simulation flow discharge. And when it's come to validation, the compromise between observation and simulation values gradually decrease, but still satisfactory within the acceptance range. As a result, the model behaves as a potentially robust predictor for flow discharge. This slide shows the results of sediment contamination simulation. So overall, we can see the sediment contamination prediction was less accurate than the flow discharge simulation in both calibration and validation. During the calibration and validation process, the sediment concentration prediction was determined to be applicable only with the killing rejection and angle hashing. So we can see more details about the statistical analysis of observed and predictive values of sediment contamination in table 6. So, and the average methods really, the value pinpoint no linear relationship between simulated and observed values of sediment contamination. So we will analyze more detail using two methods, inline hashing and killing rejection, in spatial distribution of soil erosion and deposition. So we can see that the two transport capacity methods had the same spatial and temporal dissemination of erosion and deposition, and the erosion was spot over the watershed, whereas the deposition pattern was mainly distributed along the river network, and the sediment budget results reveal severe 7 displacement from a real erosion type occurring around the basin boundaries in steep slope zones, particularly in the southeast and the northwest of the watershed. And now we take a look at the effect of topography on spatial distribution. And with slope gradient greater than 15 degrees, we can see that the box plots show the erosion, and when the eroded particle deposit on even and flatter side with slope gradient ranging from 0 to 5 degrees, and here the moderate slope areas 5 degrees to 15 degrees consider both erosion and deposition values corresponding to transition size. And conclusion. So firstly, none of the average methods achieves satisfactory results to predict sediment concentration in 3 storm events. And by allowing the adjustment of an additional parameter, the killing rejection and angle hashing methods surpass the average methods by producing more accurate results. The killing rejection also provide to be superior to the angle hashing methods, but it shows a better performance for sediment concentration simulation with a wide range of sediment size and forcing magnitude. The spatial distribution of erosion deposition outputs predicted by the killing rejection and angle hashing methods has similar pattern, while eroded size was distributed over the watershed. deposited areas were spot around the stream and water bodies. The Anglo-Haitian method illustrates the influence of topography on the distribution of erosion deposition more significantly than the killing reduction. The results also indicate that the magnitude of soil loss is mild, and slope gradient was the factor special contributing to the soil loss distribution. And results depicted that area with slope gradient ranging from 0 to 5 degrees was prone to be deposited. By contrast, erosion was likely to happen with a slope gradient higher than 15 degrees. So this is our presentation. Thank you so much for listening.
For your presentations. So, to the audience, if you have a question, please ask the question to the speaker. You can see if we have no suggestions, I will invite the next speaker. Thank you, Lynn. The next speaker is Saad Alisa. The speaker's topic is evaluating the hydrological response to climate change and anthropogenic activity in large basins using multi-model ensembles projections. Please get started.
Let me share my screen. Is there? Excuse me, you can see my screen?
I can see.
Hello?
Yes, please start. I can hear your voice and I can see your presentations.
Okay.
Yes, please.
So, this is Sabab Ali Shah from Pakistan. I am a student of PhD in Department of Civil and Environmental Engineering, Hanyang University, South Korea, under kind supervision of Professor Chewang Kim. Today, I am here to present my presentation on evaluating the hydrological response to climate change and anthropogenic activities in a large basin using multimodal ensemble projection. So these are the contents of my today's presentation. I will start with the introduction and literature review, followed by the research question, description of study area, methodology, result, and finally conclusions. So starting with the introduction, as we know, the hydrological cycle is the driving force of the physical and ecological process on the Earth's surface and have a huge impact on the survival of living organisms, particularly the human beings. The stream flow is the most important element of the hydrological cycle, and the variation in the stream flow might cause a hydrological disaster. Therefore, it is primarily important to accurately compute and forecast the temporal inconsistency in the stream flow. The experimental evidence from various parts of the globe have proven the variation in the stream flow is in the response of combined effect of climate and anthropogenic activities. The climate factors include change in precipitation, temperature, potential evapotranspiration, or etc. However, the anthropogenic activities includes change in land use, land cover, construction of hydrological structure, urbanization, deforestation, and agriculture pattern. So a rapid variation in the stream flow is rise core social and ecological issues in the various parts of the world. The accessibility and inconsistencies of the water supply stress, sustainable growth of human society have triggered global concern to quantify the effect of climate and anthropogenic activities in the watershed. Therefore, a significant attention is needed to overcome impact studies on the watershed in the large basin having the vulnerable climate condition to enhance the knowledge considering the climate and anthropogenic activities in the vulnerable water resources. This study attempts to quantify the hydrological response to climate change and anthropogenic activities in a large basin using the multimodal ensemble projection. We use a stream flow time series in combination with breakpoint determination, trend analysis, climate elasticity approach, and finally a decomposing framework. So for this study, we take the Han River Basin as our study area, and we divide Han River Basin into three major basins. As we can see in the figure 1, in the large east-north part, so we have the Buk Han River. In the southern part, we have the Nam Han River and the lower Han River Basin in the eastern part. So the mean annual precipitation rainfall and temperature on the watershed is about 1300 millimeters per year, and the average temperature is about 12 degrees Celsius respectively. So the we get the data for this study is from the Korean meteorological website for temperature, precipitation, and different climate parameters. However, the monthly discharge, land use, land cover, population data for various periods were collected from official sites of water management information system. And we also use the Hargreaves equation to generate the PET data set for our study. So the comprehensive methodology framework consists of following steps. First, we use the pipette test to identify the change or breakpoint in the hydrological series, followed by the ITI method for trend analysis. Then the climate elasticity was used to quantify the impact of climate warming and anthropogenic activities in the stream flow in different periods such as baseline period, impacted period, and future period under climate scenarios RCM 4.5 and 8.5. And finally, we use a decomposition framework to quantify and decompose the effect of each climate and anthropogenic activities on the stream flow conditions. So this slide shows the overall research framework. We start from the hydrological data set, followed by the breakpoint or change point analysis. Then the series was divided into the two different periods, such as the baseline period and post-baseline period. Then this data was used in the climate elasticity for climate elasticity coefficient calculation, and finally we calculate the difference in stream flow due to the climate. We also use RCMs, different RCMs due to data set from various climate general circulation models and downscale, and use in the same model for the calculating the impact of climate and anthropogenic activities in the future periods. So the ITI method was used to identify the trend. In this equation number 1, the plus and negative, plus and minus value indicates positive and negative trend respectively. Second, in second step, we use the pipette breakpoint change. This pipette change point considered time series into the two series, and the probability of each year change point in each year can be calculated from equation 2 and 3. Then we use the climate elasticity analysis. The climate elasticity of stream flow can be categorized as a ratio of proportional change in a stream flow to the proportional change in climate components such as rainfall and potential evapotranspiration, and can be calculated by this equation. In the climate elasticity, coefficient can be calculated by equation number 5 using the Buteyko model equations. Then in the last step, we used a decomposition framework for separating the climate change impact and the anthropogenic activities respectively. Table number 1 shows the GCM data which were used in this study for the future climate projection impact on the stream flow conditions. So the results, this slide shows the result from the pipette change point test. We determined the change in the stream flow and the precipitation in all three basins, Bukhon River Basin and Namhan River Basin shows a change point in year 1997. However, the change point in the lower Han River Basin was determined in 1995. Considering the results of this change point, we divide the whole stream flow time series into the two parts, such as the baseline period and the post-baseline period. So this slide shows the results of trend in the hydroparameter which were estimated by the using ITI. We can see in the baseline period the trend values were in negative, and however in the post change period the value were positive, which shows the shift of hydrometeorological trend from decreasing to increasing trend from baseline period to the post baseline period. This figure shows the results of land use land cover in the watershed. The watershed is primarily dominated by three types of land, such as forest, cultivable land, and the urbanization land. In table 2, we can see the compared to the baseline period, the significant reduction in the forest land and increase in the urbanization land were observed in both Bukhon River and lower Han River Basin. However, the extensive increase in the urbanization impressive and were observed in the lower Han River Basin and decreasing forest and cultivable land. This slide shows the results of climate elasticity method. The results suggest that the climate warming is key factor responsible for change in the stream flow. However, in the impact of climate change varies in each river basin, such as Namhan River Basin, Bukhon River Basin, and Lower Han River Basin. We can see in this table the effect of the climate in the Bukhon River and Han River Basin varies from 76 to 80%. However, in the lower Han River Basin, these impacts were only 43%. The anthropogenic activities contributes 24 to 19% in Bukh and Namhan River. However, the impact of anthropogenic activities were noticed leading source of penetration in the stream flow in the lower Han River Basin, which contribute about 57%. This table shows the projected climate variables. We can see we choose two future periods such as P1 and P2, and these are from 2031 to 2060 and 2071 to 2100 respectively. And these periods were compared with the baseline period, which was 1970 to 2000 under two scenarios, 4.5 and 4.8, and we can see the result in the table 4. Corresponding to the scenario, the yearly change in the P2, the precipitation is relatively greater than P1, which ranging from 11% to 13% compared to the baseline period. This result shows the future variation in the temperature. We can see the result indicate the temperature will follow increasing trend. Temperature varies in 4.5 and 4.8 was demonstrated in figure 6, which reveals that the temperature in the 4.5 will increase lighterly. However, it will increase consistently in RCM 4.8 future stream flow variation. This figure shows the impact of future climate variable on the stream flow condition. Considering the results of multimodal assemble under RCM 4.5 and 4.8, the period P1 projected the variation in the precipitation account 4 to 11%, and the evapotranspiration varies from -6 to -6.2 to -6.3 respectively. However, in the far future period or P2, under both scenarios, the variation in the stream flow was supposed to be rise from 10.3 to 10.5%, and the evapotranspiration will also be expected to increase due to the increase in the temperature in P2. It will be account from 11 to 16%. These variation in the future climate factor might lead the alteration in the stream flow in the basin. The projected variation in the stream flow in table 6, we can see that during the P2, it will remain 23 to 27% concerning to the baseline period under the RCM 4.5 and 4.8. The overall results, the conclusion were drawn as shown in this slide. The significant variation in the climate factor observed in and which disturb the watershed stream flow. Rapid variation in the anthropogenic activities may cause significant alteration in the stream flow, result in hydrological disaster. Might be a result of hydrological disaster in the basin. The hydrological change point was inspected in 1990s, which was taken as a point of start of anthropogenic activities in the basin. The contribution of climate and climate change still remain major factor responsible for change in the stream flow. The result obtained from different models, the climate change variability was observed leading influence in stream flow condition in the watershed, which accounts 70 to 90% of total change. However, in the lower Han River basin, the scenario was changed. The anthropogenic activities remain primary factor in this basin, which contribute 57% of total change in the stream flow. It might be a cause of extensive increase in the land use and land cover in this area. We extended our work to evaluate and decompose the hydrological response to climate and anthropogenic activities for future climate scenarios, such as RCM 4.5 and 8.5. The variation in climate factor would affect more in the future, ranging 23% to 27%. These findings of this study will provide advanced knowledge to the researchers, hydrologists, experts, and regional water resources management for designing future disaster mitigation plan and decision making considering the climate change and increasing anthropogenic activities in the basin. Thank you for your attention. Any questions are welcome.
If you have any question, please. First, actually, the time is very limited, so I'm sorry, sir. I passed the Q&A time. Sorry. And thank you, Mr. Saab.
Thank you. Thank you, Professor.
The next speaker. Next speaker is the Doan Tai Tu Ha. The topic is the advanced in real-time of flood forecasting with this computational risk acquisition and accurate uncertainty quantifications. Please get started.
Sorry, Mr. Chairman, maybe in the next presentation is mine. The advances in real-time urban flood forecasting, right?
Can you? Hello?
Sorry?
Mr. Ha?
No, I'm from University of Ulsan, and I have a presentation in the fourth place, right? Advances in real-time urban flood forecasting.
Yes, advanced in real-time urban flood forecast,
Yeah.
right?
Yes.
Yes, please get started.
So can you see my presentation?
Yes, I can see, I can
Yeah, thank you.
very
So
well.
first of all, my name is Trần Ngọc Vĩnh. I'm from Vietnam. Currently, I'm a fourth year PhD student in the University of Ulsan, and my advisor is Professor Professor Kim Jong Ho. Yeah. Now I want to start my presentation. My presentation have six main parts. The two first part I want to define the problem, and the third part I want to give our motivation on the research, and the fourth and the five and the sixth parts I want to present some methodology and results and conclusion. So going to the first problem is of our recent research is flood. And flood, we all know that flood is an overflowing of large amount of water beyond its normal confines, especially over what is normally dry land. So flood can be divided into two types: river and fluvial flood, and urban flood. A river flood occurs when the water level in a river, lake, or stream rises and overflows onto the surrounding banks or neighboring land. And the second type is urban flood occurs when the inflow of storm water exceeds the capacity of a drainage system to infiltrate water into the soil or to carry it away. Both types of flood can be happening with situations like a river crossed an urban areas during the heavy rainfall, for example. So for the flood season, the most flood events happened due to the heavy rainfall, that up to more than 90%. Other reasons can be related, such as dam break, snow melt, or storm surge. So normally for the same event as flood, the probability of flood occurring in the pluvial and urban area is different. Specifically, in areas that are considered natural, like forests, mountains, the roadways are higher than that in the urban areas. So the probability of the flood is less than in the urban area. So why flood is concerned? Because flood is one of the most disaster over the world that is most happen among many disasters like earthquake or tsunami, for example. So the flood happens when we look at this figure, we can see that the flood happens all parts of the world, especially for the South and Southeast Asia, like Vietnam, Thailand, China, Myanmar, and even South Korea. So from 1985 to 2020, the number of extreme floods that was increasing trend from the 10 to another 50 floods event per year. So we can see that the ratio of the extreme event, the red line here, also increased from 0.2 to 0.4. It means that for example, if we have 10 events or rainfall events, we have more than 2 to 4 events that are extreme, that significantly damage. So why we call flood a disaster? So this is because of the consequences of flood are extremely terrible, like floods, infrastructure damage, fatalities, economic losses, and decent food. So another, for example, in Vietnam, so within 20 days in October last year, so 4 storms hit central Vietnam, causing historic floods with a frequency of more than 100 years of return period. The result is widespread flooding throughout central Vietnam, leading to landslides, flood. So So some information we observed that the observed rainfall is up to more than 1,700 millimeter on only 3 days. The number of homes, the number of houses destroyed was over 2,000, and the number of fatalities is over 300 people, and a lot of crops and cattle and poultry were losses. So from these disaster and consequences of floods, so we can see that flood forecasting can be flood forecasting play very important. So flood forecasting can be defined as the process of estimating and predicting the magnitude, timing, and endurance of flood. So with the aim of prevent damage to human life, to the oil and the environment. So the input of the flood model, also I call it the model flood model, like the common name, like to the input, this model requires the most important factor is the rainfall. This is focusing some information of the area like DM, terrain, land seal, soil type, and some information of the house or streets like this. So, many water sets characteristics cannot be measured, like roofage, hydraulic conductivity, for example. So these parameters normally cannot be observed. So we have assumed these factors into the model. So finally, we got the results of the model, and we can see that the model prediction have a lot of uncertainty that came from the unknown parameter, and the forecast rainfall that have a lot of uncertainty. So here I would say that for the flood forecasting, we have two big problem. Big problem is flood prediction is usually inaccurate, and uncertainty quantification of the possible rainfall and the parameters is essential. So however, quantifying the uncertainty is not easy, because the uncertainty is come from the rainfall and the parameter, as I said, and is lead to large uncertainty. So especially for the model parameter, to find the good parameter, as we know, the most common approach is using some Bayesian inverse approach, like optimization, uncertainty quantification, sensitivity analysis, and data simulation. But these methods require many model runs, so it will be very computational burdens, especially when we use the physical-based model with hours for each run. Even we use the multi-core workstation or even parallelization. So here we can define two big problems in flood forecasting. The first is large uncertainty exists in prediction, and the second one is computational barriers exist in real-time forecasting with uncertainty quantification. So from this problem, so I defined and I define my motivation is, the first one is to reduce the uncertainty in prediction, and the second one is to break down the computational barriers in uncertainty quantification. So for the motivation and for the research scope, this is a framework of the ensemble prediction that I was developed, including the input forcing in initial state parameters. This is for the input, and the method here is used for the parameter visualization and the model. So for our main focus, I want to focus on this part and this part, which parameter realization is used to increase the model accuracy, and the model part is used to increase the model efficiency. So next one is methods. So I would like to talk about urban flood model that we have developed recently. So probably call it is the urban flood model because we haven't decided on it. So UFM can be divided into 3 groups. As we know today, the first group is comprehensive model that can simulate most of physical processes, water transport and water exchange from rainwater to sewer or stormwater system. This type of model can show inundation depth in both considered as overland oriented and drainage oriented. And the second and the third types of UFM perform the water flow down to the drain first, and then if the surcharge happen, the 2D model like a third flow or the another 2D model will be simulate. So the different type 2, 3 is that the type 2 model consider the flow condition of the surface ground flowing back to the manhole, but the type 3 of the model, this one, is only combined one way from the manhole to the ground surface. And this model didn't consider the condition of the flow in the ground surface flow back to the manhole. So the model we built includes 3 main components, including rainfall runoff model, overland flow, and stormwater model. This require for the input is required topographic data, severe data, rainfall, and initial model like water levels. So regarding processes, this model compute the amount of water flowing on the road surface or the roof after move to the seepage or infiltration. So the water in surface will be computed in 2D model and flowing down to manholes. So at this time, the 1D model will simulate the flow along the conduits.
Mr. Trump, please close in 2 minutes. Please close your presentation in 2 minutes, please.
Sorry?
Please close your presentation in 2 minutes. It's a time is over.
Time is over?
Yeah, so but I give you 2 minutes more. Please. close your
Okay,
presentation.
okay. Oh, I am now. Let's move to the results. This one first. So another method is I want to propose the novel real-time flood forecasting framework that including 3 parts. The first part is the surrogate model that can significantly improve the model efficiency, and another part is the uncertainty quantification and data simulation to increase the model accuracy. So by using the surrogate model, we can significantly increase the efficiency by can enhance more than 3 million times faster than the physical-based model. This one. So because I only have 1 minute, so I want to move to the results quickly. So this is the results. We compare the surrogate model and the original model, this physical-based model. So this one we can see that if we use physical-based model, it takes a lot of time, maybe more than 3 hours for one simulation. But when we construct the surrogate model, this model can significantly reduce and speed up the runtime with less than 1 second. So we can see that more than 3 million times speed up, and this surrogate model allow for real-time forecasting. So the main our conclusion is we propose new model based on the new urban flood model, based on the rainfall runoff model, open rainflow model, and conduit flow model, and a novel modeling framework for computationally efficiency and accurate real-time forecast were proposed based on PC specification and data simulation. And our approach is highly increased the accuracy and enhance significantly the model efficiency. So this is our main presentation. Thank you. This is our publication for my presentation.
Yeah, it's very good. So thank you for your presentations. Due to the limited time, we discuss with yours presentation later. Next,
Yeah.
thank you.
Yeah, thank you.
Next speaker is Swandi Chandrasekhara, yes, at Sejong University. The topic is developing osmotic scale surrogate model to estimate reference yield for transpiration. Please get started. Swandi? Swandi? Hello? swandi? 저기 세종대학교 학생 혹시 있나요?
저기 세종대학교 써져 있는 사람한테 물어볼까요?
네. I'm sorry, sir. One speakers does not respond. I'll wait just a little bit. 세종대학교 학생들 혹시 있나요? Okay, so I'm sorry, the speaker, one speaker does not respond. So our session will be closed now. So thank you for your presentation. So I'm very appreciative for speakers. And I want you to keep your research going well. So, if we have a chance, we discuss your researches more deeply. Thank you for attending this session. So I close this session. Thank you.
Thank you, Professor, for giving us time and opportunity to present our research. Thank you so much.
Okay, thank you.
Thank you, Professor.
Thank you.